Okay, so let's continue on with our lecture of chirality, and what we're next going to discuss is this idea of optical activity. How do we get a sense of whether molecules are chiral or achiral just looking at bulk samples of material? Well, first and foremost, let's switch the drawing tool. So light restricted to pass through a plane is known as plane polarized light. A polarimeter measures the rotation of plane polarized light that has passed through a solution. The source passes through a polarizer and is then detected at a second polarizer. And the angle between the entrance and exit planes is known as the optical rotation. So, a key difference between chiral and achiral compounds is that plane polarized light that passes through solutions of achiral compounds will retain its original plane of polarization. However, if plane polarized light passes through a solution of chiral compounds, these solutions of chiral compounds actually rotate plane polarized light, and that's why the molecules are said to be optically active. Okay, so the way that the overall optical rotation of a sample is measured as units of degrees, it's known as alpha. Clockwise rotation of plane polarized light is known as dextrorotatory, and it's depicted with a positive sign for your optical rotation, while anti-clockwise or counterclockwise rotation of plane polarized light is levorotatory. It's depicted with a negative sign for your optical rotation. Now, the specific rotation, alpha d, is a standard measure of optical rotation, and quite simply, it's taking the observed rotation, accounting for the path length of your cell and the concentration of your solution. Specific rotation is typically observed for 1 gram per mil in solution for a cell with a 10 centimeter path length using light from sodium metal vapor. Most of the instruments are standardized for measuring specific rotation such that you won't actually have to use this equation very often. Now, an important thing to keep in mind is that specific rotation of enantiomers is equal in magnitude but opposite in sign. And the other thing I do want to caution about is that specific rotation, the sign for specific rotation is not correlated with any given stereochemistry. There's no consistent relationship between R and S stereochemistry and whether you observe a positive or negative optical rotation. So, for example, if we compare SS tartaric acid with its enantiomer RR tartaric acid, the SS enantiomer has an optical rotation of -12, while the RR enantiomer has an optical rotation of +12. Enantiomers have the same magnitude for optical rotation, but opposite sign. Okay, because the optical rotation is negative in this case, we call this minus tartaric acid. Because the optical rotation is positive for the RR tartaric acid enantiomer, we call this plus tartaric acid. Okay. Now, I really do have to stress that there is no simple relationship. There's no simple relationship between RS and the direction of optical rotation. Now, even additionally, the sign of optical rotation can sometimes change based on the solvent, concentration, and other factors. Specific rotation is compound and temperature dependent and must be determined experimentally. So for example, let's look at a range of molecules, each with a range of chiral centers. And you notice that the optical rotations vary pretty dramatically between compound and vary pretty dramatically depending on the solvent. However, one thing that I do want you to pay attention to is that for these two compounds, chloroform and acetic acid, so chloroform, which looks something like this, and acetic acid, which looks something like this, both of these two compounds are achiral, and as a result, their optical rotation would be 0. So that is one thing to keep in mind. So achiral compounds will not rotate plane polarized light. So measurement of optical rotation can give you a sense whether or not your compound is chiral. Okay, so moving on. Enantiomeric excess is a really critical idea, and it's a really commonly reported value to help assess the potential selectivity of certain reactions. So in many cases, one enantiomer of a compound has a greater biological activity or even has the desired biological activity at all. So biological systems and receptors are chiral. We, as organisms, are composed of chiral molecules arranged to generate chiral structures. And because these biological systems and receptors are chiral, just like your hand can determine whether you're shaking someone's hand with the left or right hand, these receptors can differentiate compounds based on their configuration and shape. So fundamentally, one of the building blocks for large-scale proteins and peptides are amino acids, and amino acids are chiral. And just as an interesting piece of trivia, all of the amino acids have an S configuration except for cysteine. And we'll talk about why that is when we discuss the priority measurement to assign R and S configurations. So essentially this idea based on like lock and key, different molecules have different binding affinities and bind to different receptors based on their configuration and shape. Depending on the arrangement of their substituents, they can fit into different receptors and fit in certain receptors with a greater binding affinity. Just like if you're shaking hands, for example, if you use your right hand, for example, your thumb's right here, and if you're shaking hands with someone's left hand, for example, you'll instantly be able to recognize, because when you shake hands, your fingers will line up in a slightly different way. That's the analogy that I like to think of this. You can also think of it as like one of those children's toys where they have like a square peg and you have a square hole and things fit if all of your substituents are in exactly the right spot for productive binding. So depending on the stereochemistry, depending on the relative arrangement of your substituents, you can end up with different binding affinities and different biological activities for different enantiomers. Okay. So a classic example is looking at ibuprofen. Only the S enantiomer of ibuprofen is biologically active in terms of its beneficial effects. The R enantiomer is inactive. Even more interestingly, for penicillamine, which was primarily used for treatment of arthritis before more effective medications were developed, the S enantiomer can be used to treat chronic arthritis, but the R enantiomer is actually highly toxic. So you do want to have tools available to determine the relative amount of each enantiomer in a mixture, because you want to be able to see whether your method to separate enantiomers has been done effectively and whether a reaction to generate a single enantiomer has efficiently generated just a single enantiomer. So we need methods to determine the purity and amount of each enantiomer in a mixture of enantiomers, because enantiomers have different activity, and it's really critical to understand whether your reactions are efficiently generating your desired enantiomer and how much of the undesired enantiomer is present in your mixture. So the first measure of enantiomeric purity is enantiomeric excess. I personally prefer enantiomeric excess over other measures of enantiomeric purity. It's best defined as the percentage of desired enantiomer minus the percentage of the opposite enantiomer. So for example, let's suppose a reaction generates 70% of the desired R2-butanol and 30% of the undesired enantiomer. So our EE in this case would be 70% for our desired minus 30% of our undesired, and that gives us a 40% E, which is not great, to be honest. Now, the other method of measuring the ratio of desired to undesired enantiomer, although I personally don't prefer it, is %EE, which is a measure of the percentage of the desired enantiomer. So quite simply, you take the observed optical rotation, divide it by the optical rotation of the pure enantiomer times 100%. I personally like enantiomeric excess, as often we're looking to see how efficient our separation was at generating an excess of our desired enantiomer, or how efficient our reactions are at generating an excess of our desired enantiomer. Okay, so these are our two methods. So if we're given a mixture, we can certainly calculate the enantiomeric excess and the %EE, and it essentially gives us a gauge of how much of our desired enantiomer is present in a mixture. Okay. What we're next going to talk about is the systematic process for assigning the configuration at chiral centers. So we're going to use the Cahn-Ingold-Prelog System, and this is based on the IUPAC framework. So first and foremost, we're going to look at the 4 atoms directly attached to the chiral center, and we're going to rank them according to atomic number. So in terms of our priority, the atom with the highest atomic number is assigned the highest priority. The atom with the lowest atomic number is assigned the lowest priority. So for example, if we had to look at the following molecule here, the atom with the largest atomic number is bromine, so that'll be our 1. Next up is chlorine, that'll be our 2. Carbon would be number 3. And hydrogen is number 4. Perfect. So looking at the molecule on the right, sulfur would be number 1. Fluorine would be number 2. Oxygen would be number 3. And hydrogen would be number 4.